First, I do want to put out a warning to all of you as the experiments in this video involve using high voltages that are lethal if not handled correctly. And I strongly discourage anyone without the proper knowledge and equipment to conduct any experiments with high voltages. So I was experimenting with some of the high voltage stuff and wanted to have a way to reliably discharge the high voltage capacitor and dumping the energy into the load connected. Besides some of the obvious fun factors, such as destroying stuff, fast and efficient discharging high voltage capacitors have some very important real-world applications. For instance, in radar systems, we can operate pulsed magnetron, which is capable of generating megawatts of RF output power this way. Now, of course, you could just simply connect a high voltage directly to the load, as you have seen in many of the YouTube videos, where the YouTuber uses a long insulated rod, aka high voltage discharge stick, and move the wire into contact with whatever the circuit is. And of course, in the process, you would hear this loud bang when the capacitor discharges. While this approach makes it more dramatic, there are quite a few drawbacks. And the main issue here is that a lot of the energy is wasted in the process of sparking and not ended up in the load. Of course, the spark also creates ozone, which is harmful, and there is also the noise pollution risk and risk of flash burn and fire hazard, and so on and so forth. A slightly better approach would be to use some kind of spark gaps, and you can often see this approach being used in the construction of larger Tesla coils. Although spark gaps offer more precise controlled discharge, the previously mentioned drawbacks remain valid. So what about semiconductor devices? And indeed, high voltage silicon controlled rectifiers, triacs, and IGBTs would be ideal in handling this kind of high voltage, high current situations. But trying to get a device that can withstand more than a couple thousand volts and tens of amps can be quite expensive and easily beyond the reach of hobbyists. And also, semiconductor devices are not robust enough and could easily be damaged in overcurrent situations. So in fact, before I started making this video, I was doing some experiments with this IGBT device. And by the way, so this IGBT is a QIS series, now is long obsolete, but this one does handle over 2000 volts and I think it's a 25 amps maximum load. Now in comparison to the standard TO220 packaging, which is I have here on the left, you can see how big this device is. Unfortunately, this device is rather fragile, and I was using it to conduct some experiments, and it all went well, but unfortunately, a couple of misfires damaged this one and also damaged another one. Now, these devices, even though now you can get it for around $20 if you look carefully on eBay, but they generally come quite expensive. They're sometimes over several $100s a piece, and of course, one mistake is all it takes to take this device out. So that is what brought us to the main topic of this video. And what I have here is a Hydrogen Thyratron, and this is a TGI 1-50/5. It's a Russian tube, and so its base specification is listed here. Of course, I have looked around on the internet, and the only thing I could find is this data sheet, which is Russian. But of course, I don't speak Russian, so luckily we can easily translate that back to English using the Google Translate. And here is the translated version, and basically you can see that this one is really quite beefy, actually, the device. It requires a filament voltage of 6.3 volts and draws about 3.2 to 4.1 amps with the hydrogen generator, which I'm going to touch upon just in a short while. And it can handle pulsed anode current of up to 50 amps. And let's see what else is important here. Of course, you can have 4,000 impulses per second, which means the maximum operating frequency is about 4 kilohertz. And there's some other important aspect that we need to pay attention to. For example, the voltage that is needed to trigger it should not be less than 150 volts. So this is basically for the grid firing pulse. And let's see what else. We also have that the anode direct and reverse voltage, the maximum is 5 kilovolts. And so that's pretty much what we're looking at here. So now when we look at this Thyratron, and for those who have never used a vacuum tube, and especially a Thyratron before, and by the way, the Thyratron itself is actually very similar to the operation principle of a silicon controlled rectifier. For instance, we have this grid pin that is number 4 denoted here. This really is kind of similar to your gate. So if I have to draw it out, let me just draw it here. So you have in general, a silicon controlled rectifier. You have a gate, and this anode and cathode. So whenever you apply a current through the gate, that will turn this silicon controlled rectifier conductive and allowing the current passing through from anode to cathode. Whereas for a Thyratron, the similar principle holds, except it's a voltage control device. So if we apply a voltage at the grid, then the Thyratron would start conducting between the anode and your cathode, which is pin number 1. Now for this specific tube, it also has a heater element, which is between pin 1 and pin 2. And it also has a so-called hydrogen generator, which is pin number 3. So let's take a look at the hydrogen generator here. And the reason this is called a hydrogen Thyratron is because it is using the hydrogen ionization process as the conducting mechanism. Like all the gas discharge tubes, the hydrogen Thyratron is not entirely vacuum inside. It utilizes its working medium, in this case hydrogen, as the discharge medium. So let's take a closer look at the mechanism for generating the hydrogen. And in here, you can see that we have this little cylindrical component inside this tube. This is actually what the hydrogen generator is. So in a typical discharge lamp, if it is for example, mercury vapor lamp, in its cold state, you will see some mercury condensed on the side of the tube. And when you heat up the tube using the cathode, and the mercury would evaporate and forming the working medium. But in this case, it works in a similar fashion, except that what is inside the cylinder typically is a compound called the titanium hydrate. And so titanium hydrate has the property, let's take a quick look here. So typically it's titanium with hydrogen bound to it. So there could be 1 or 2 or more. And when heated up, this basically turns into titanium metal plus some hydrogen. So, and the hydrogen would be released into the tube, forming the working medium. So this is when it's heated up. And when the tube is cooled down, the whole process reverses itself. So it goes back, the hydrogen would go back into this titanium hydrate form. And that's the that's complete the cycle. And because we have a hydrogen generator inside, we not only need to apply the filament voltage, we also need to apply voltage to the hydrogen generator as well. Unfortunately, I couldn't find exactly what the voltage is for the hydrogen generator. It only mentioned that the filament is 6.3 volts. And I assume that the hydrogen generator is also around 6.3 volts, even though it has its separate pin. Now, a typical Thyratron what you can do is you can adjust the hydrogen generator's voltage to determine how much hydrogen you want it to be inside this tube, and that could adjust the sensitivity of the firing of your Thyratron. So in general, I read in the literature somewhere, basically what you can do is you can start to increase the voltage till the tube started to self-firing, and then you can dial back down the voltage to make sure that the firing stops before you applying the firing pulse at the grid. So now, of course, we want to start experimenting with just applying a 60.3 volts and to see how it goes. And if we have issues, we can adjust the actual voltage to get it back into the working condition. But all in all, this is what is inside a Thyratron. And you can see that it's actually quite beautiful looking. And in operation, we should see some hydrogen discharge glow if we can get this thing to work. Before I start the experiment, let me show you the circuit diagram that we're dealing with today. And here, as you can see, at the center of the circuit is our hydrogen Thyratron, and this one is a TGI 1-50/5. It's a Rosen tube, as we saw earlier. Now, here the anode is tied to the 3,500 volts power supply via a 100 ohm power resistor. And the reason we need this resistor here is because the maximum operating current through the anode is at 50 amps. So we wanted to limit that so that we don't destroy the tube. So 100 ohm would be well within the 50 amps envelope. In fact, it would be maximum of 35 amps. And the heater situation here, I actually draw it out like this. Basically, we have a standard heater, which is a 6.3 volts, and we have another heater for the hydrogen generator. So we could just tie these two together and supply a 6.3 volts to both the filament and the hydrogen generator. But I wanted to make sure that we can actually adjust the voltage to the hydrogen generator to make sure that the pressure inside this tube is operating at its optimal pressure level. So that's why we have a two 6.3 volts, and this 6.3 volts for the hydrogen generator can be adjusted up or down depending on what we find what's the desired operating condition here. To fire the Thyratron, we need a pulse into the grid, and this pulse is actually specified in most of the data sheets that you can find with the specific Thyratron you're using. Typically, the requirement is such that the pulse has to be has a very fast rising edge so that it can trigger the Thyratron reliably. Now for our experiment, we're just going to use a manual switch. So here we have a small capacitor, it's 100 nanofarad. What we do is we use this to charge up, and using that pulse to trigger the grid. So here is a 27K resistor from the grid tied to the ground, and note that we also have a resistor across the capacitor. Because we're arranging this capacitor in this way, there's no way for the capacitor to self-discharge. So that the resistor is needed once that we release the switch, this capacitor would be self-discharging through this 1 mega ohm resistor so that we can fire again if needed to. So as you can see that the circuit is really simple. In fact, it doesn't get any simpler than this. Of course, depends on the Thyratron that you're using. It may need a negative grid bias. Now this one, as you can see, the bias is 0 because we tied it to the ground. Now I don't know whether or not this will work for this Thyratron or not, but we can certainly test it out, and if it doesn't, we have to revise the circuitry. Of course, that will add a little bit of complexity here, but in general, this grid needs to be negatively biased, and then a positive pulse rises, triggers the conduction of the thyratron. So let me build this circuit up, and we will take a look. And here you can see the overall experiment set up. And at first it does look a little bit complicated, but I'm going to walk you through component by component, and hopefully you will see that it's actually quite simple. Now, you do notice that everything is on top of very thick styrofoam, and the reason for that is because I want to make sure that the high voltage stays away from any region that can possibly cause a discharge. And the first part is the high voltage part, and as you can see here, we have this voltage doubler here, and the input is from this transformer, and I will show you. So these two leads output roughly 1700 volts, and it passes on to this voltage doubler. And underneath here, I have this large capacitor is 2 by 3.5 microfarad, rated at 2000 DC. So this 1700 roughly, the voltage get doubled, and the output is roughly 3500 volts. And also you notice that we do have bleed resistors for each of the halves of these capacitors. So this one capacitor is actually two halves. It's just kind of like your center tapped transformer, except this is a center tapped capacitor here. And the output of that high voltage is here, and through this high voltage wire and this 100 watt 100 ohm resistor, and it goes through a circuit board with this jumper wire. And the reason I have it here is because later on we can hook up some device here to test that having a pulse going through this device under test. But now we have it shorted, so this essentially just going through this resistor here and goes to the anode of this thyratron. And now let's take a look at the triggering portion of this circuit. So here I have another transformer. This one outputs about 200 AC and into this full bridge rectifier and a filter capacitor here. And here is a lead resistor. So whenever you're dealing with high voltages, always make sure that the capacitors have at least a lead resistor on, because otherwise the capacitor will remain charged for a long period of time after the power is removed, which can be very dangerous. And the output of this, so this black wire is a ground side, and the red wire here is the positive. So this goes through a switch, and as you can see, this is not very beautiful, but it makes the job done. So it goes through this wire, goes through this capacitor. Again, I have a bleed resistor in parallel with it, and this one goes to the grid, and the other side we go to the ground. So this is the triggering portion, and the remaining wires are actually to deal with the hydrogen reservoirs heater and also the filament heater. So as you can see, the three wires, 1, 2, 3, the two red ones and this black one are the heater wires. So as you can see here, we have two sets of alligator clips. They come in black and red, and these are the two sets of 6.3 volts supplies. And also I'm using two separate power supplies. One is the emerald supply back there, and the other one is that lambda power supply back there. So these two currently set up for both 6.3 volts, but as I mentioned earlier, we can adjust them as needed, especially for the hydrogen reservoir power supply. And that's pretty much the setup. So now let me power up the power supply, and we can take a look at this thyratron in action. So now I'm going to power on the filament supply voltage. And now it's just gradually warming up. At some point you might be able to see some the filament lighting up, but not sure if you can see from this angle. Let me take the camera from the other side. You can probably see it a little better. So now you can see that there's an orange glow inside. That's the filament. So let me put it back so we can see the rest of the setup here. The next, what I'm going to do is I'm going to turn on the hydrogen reservoir power supply. And as you can see that we do have both power supply on now. So after I warm it up a little bit, I'm going to turn on the high voltage supply. And this is where it's going to become dangerous. But again, as we mentioned earlier, we just need to be very careful when dealing with high voltage systems. And I cannot stress the safety precautions enough. And now that the tube had warmed up sufficiently, I'm going to power on the high voltage power supply. And you might hear some hum. That's the transformer, which is normal. 3, 2, 1. So now the high voltage is energized. So just to test the high voltage portion, I'm going to hook up this meter here, and just going to show you. This is not necessary, but I want to nevertheless show you. So we have a, so let me put it here. Let's turn to, by the way, this is hooked up to a 1 to 100 probe here. And I'm going to test the voltage output from this device here. So just let me get my hand around here so I don't poke. And you can see this is showing 34.3, which is roughly 3,400 volts. And so it's not quite 35, but give or take, it's in the range. Okay, so now let me disconnect this one and move it away. So now the Thyratron would be ready to fire. So what I'm going to do is I'm going to press the button here. So as you can see, we do have a momentary button on the side. There's a momentary button here. So when I press this button, you should see the glow inside the Thyratron tube. 1, 2, 3, go. So the first one is actually, you saw a little bit of spark. That's because the contact of that anode clip is not very well clipped on. But now, after it's after we fired it once, now it's very securely clipped on. And let me just zoom into the Thyratron, and you can see the pulse here. So I'm going to fire it. And you can see that every time we fire, we have this beautiful bluish glow, which is the energized hydrogen ion inside. So, and make no mistake, actually whenever it fires, there's actually quite a high current going through. So the Thyratron is able to conduct tens of amps without any issue, and you barely notice any problem here. And you barely notice anything except that glow that you can see whenever the Thyratron is triggered. So what I'm going to do next is to hook up. Remember what I said earlier about this board here is that I can use this to hook up a device under test, and you can see the current flowing through that device under test. So now let me turn off the high voltage circuitry, and I'm going to fire the Thyratron one more time so that make sure that there's no high voltage. And then I'm going to hook up a resistor in that board setup. Okay, so what I have here is a 100 ohm resistor. So what I'm going to do is I'm going to put it here instead. Okay, so the 100 ohm resistor. And I'm going to zoom in onto that setup so that when I power it up, you can see what the current does to the resistor. Okay, so now I'm going to turn on the high voltage again. And now I'm going to press the trigger button. 3, 2, 1. And you can see that it's actually quite dramatic. Okay, so now let me replace that with a different one. And we'll see the same experiment again. So now this is a fresh 100 ohm resistor, and I'm going to put it here, and I'm going to turn on the high voltage again. So now we're going to trigger the Thyratron. 3, 2, 1. Wow, that was loud. And that is pretty much what I want to show you in this video of the operation of a hydrogen Thyratron. I hope you liked the video and learned something new. If you enjoyed the video, please give it a big thumbs up. Remember to share, subscribe, and I will catch up with you next time.